sound suppression water system arm. T minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and liftoff of Space Shuttle Atlantis, the final visit to enhance the vision of Hubble into the deepest grandeur of our universe.
Explorations of space end on a note of uncertainty, necessarily so. We are, by definition, in the very center of the observable region. We know our immediate neighborhood rather intimately. With increasing distance, our knowledge fades, and fades rapidly. Eventually, we reach the dim boundary, the utmost limits of our telescopes. There we measure shadows, and we search amongst ghostly errors of measurement for landmarks that are scarcely more substantial.
Ready, Drew? I'm ready, John. Let's go do this. Oh, this is fantastic. You're gonna love it, Drew. Looks nice.
Why do we go to the bottom of the ocean or the top of the sky? Why do we explore in the first place? It's humanity's ongoing pursuit of the unknown that drives us to explore the universe, to unlock its mysteries. We don't have to travel far to be immersed in the unfamiliar. The universe holds many secrets, and we are in a golden age of discovery. Decoding these secrets is what drives astronomers to peer into the darkness of space. Light from the most distant objects reveals the structures of our universe. Inevitably, we stumble upon the story of our cosmic origins. Our story begins over 10 billion years ago, when the universe was still adolescent. The ancestors of today's galaxies roamed the cosmos, forged in a time of immense struggle between forces that continue to govern our universe to this day. With a large and hungry black hole at its core, this galaxy is known as a quasar. It's among the most energetic phenomena in nature, outshining our sun 1 trillion times over. The jets you see emanating from this quasar get their energy from matter falling into the supermassive black hole at the center. Are these quasars and other galaxies solitary groups of stars? Or are they islands within a huge ocean? Astronomers want to know what the vast spaces between galaxies contain, and how these become the birthplace of galaxies, stars, and planets. In our journey from this quasar back to the Hubble Space Telescope, we are going to investigate how light changes as it travels across the universe. The light that leaves the quasar has many colors or wavelengths, both visible and invisible. When we spread light out to study its component colors, we call it a spectrum. Certain colors are bright. We call this an emission spectrum. The information from billions of years of interactions with gas, dust, and other galaxies gets encoded into the light, changing the spectrum as it travels toward Earth. To help us visualize this trek, we will study and record the spectral changes. The spectrum from the quasar includes emission lines. These act like cosmic fingerprints that pinpoint the composition of the quasar itself. Studying the light and the information embedded within it is the key to unlocking the cosmic code. Using these spectral fingerprints, we can discover what planets, stars, and galaxies are made of. In the 17th century, Isaac Newton put light through a prism and showed that white light is made up of all the colors of the rainbow. Light is sometimes described as waves of energy that move through space. Long wavelengths look red and carry less energy. Short wavelengths look blue and carry more energy. We see light as varying intensities of colors. This visible light is but a fraction of the entire electromagnetic spectrum. Most of the universe is illuminated by light that we can't see. It exists beyond our sensory perception. Since we can't directly see it, we build instruments to detect what is otherwise invisible. A few centuries later, Joseph Fraunhofer added to Newton's discoveries when he built the spectroscope. He placed a slit between the light source and the prism. This revealed the spectral lines hidden within the light. It was our first glimpse of the cosmic code. Shortly thereafter, Gustav Kirchhoff and Robert Bunsen discovered that the spectrum of gases is different from that of ordinary white light. They discovered that each element has its own unique set of emission lines. These spectral lines represent the chemical composition of the gases. They provided the key to unlocking the cosmic code. Much the way everyone on Earth has fingerprints unique to themselves, elements have their own cosmic fingerprints embedded in the light. To reveal our cosmic origins, we need to follow the quasar's light back to Earth and unlock the cosmic code embedded throughout its journey. We are now 1 billion years into our journey back home. Our instruments have detected an invisible gas cloud. How do we know that? Compare the spectra we just detected to that of the quasar. Note the differences. The quasar spectra are called emission lines, and the new spectra are called absorption lines. When light passes through hydrogen gas, the gas absorbs those frequencies of light, leaving a gap in our spectra. That's why you see missing lines when looking at absorption spectra. When hydrogen atoms are highly energized, like in a quasar, they emit light at these specific frequencies. Whether it's absorption or emission, the cosmic fingerprints remain the same. The first stars and galaxies formed out of large clouds of hydrogen gas, thousands of light years across. These gas clouds slowly condensed under the force of gravity, igniting generations of stars. Let's leave this gas cloud and continue on our long journey back to the Hubble Space Telescope. We have now been traveling for half the age of the universe, roughly 7 billion years. Our beam of light is passing near a galaxy. What can this galaxy tell us about the composition and structure of the universe just a few billion years from present day? As it passes by this galaxy, the spectrum has become more complex. We see codes of carbon, oxygen, nitrogen, iron, and trace amounts of other elements. These elements have taken billions of years to form. But where did they come from? The answer can be found inside the galaxy itself. all of the elements essential to life, carbon, oxygen, calcium, and iron, are forged through nuclear reactions in the hearts of stars. Our Sun is a medium-sized star that is 4.5 billion years old. It represents 99.9% of the mass of our solar system. Currently, our Sun fuses hydrogen into helium in its core, and it's roughly halfway through its 10 billion year lifespan. When the Sun runs out of nuclear fuel, it will swell up to form a red giant. The outer regions will expand, while at the same time gravity compresses and heats the core. Fusion in the core of red giants turns helium into carbon. At the end of its life, our Sun will become unstable and slowly puff its outer layers away, distributing these elements into the galaxy. There are stars much more massive than our Sun, like Betelgeuse. More than 20 times the mass of the Sun and 700 million miles in diameter, Betelgeuse would fill up our solar system out to the orbit of Mars. Massive stars have stronger gravity, whose immense force compresses and heats the core, creating the heavier elements, such as oxygen, silicon, magnesium, and iron. The very existence of the solar system, Earth, and even life, was dependent on supernovae to disperse the heavier elements throughout the galaxy. When these massive stars die, they blow apart in giant supernova explosions. The Hubble Telescope has documented the wide variety of star deaths throughout the universe. From cataclysmic supernovae that produce remnants like the famous Crab Nebula, to the death of stars like our Sun that produce the Cat's Eye and other planetary nebulas. These observations give us a unique glimpse into the origins of matter. Instead of a white dwarf that is left at the core of planetary nebulas, the most massive stars leave behind neutron stars and black holes. These supernova explosions blast gas all the way out of a galaxy, and that is the gas our beam of light passed through. This process recycles gas on a cosmic scale, distributing elements throughout the universe. Hubble has also investigated the humble beginnings of stars in stellar nurseries, like the famous Orion Nebula and the equestrian-looking Horsehead Nebula. These giant molecular clouds are tens of light years in size and grow to be hundreds of thousands of times the mass of our Sun. Inside these clouds, entire clusters of stars are born. Our Sun is likely an ejected member of such a cluster of stars. All these newborn stars and their dead counterparts are contained in galaxies like our own Milky Way. There is a wide variety of galaxies in space, like the Whirlpool Galaxy and the unmistakable Sombrero Galaxy. The pinks and blues you see are star-forming regions within the galaxy. Some of them may have easy-to-see spiral arms, while others look like an amorphous blob of stars. One thing they have in common is that they all have a supermassive black hole at their core. Some of these galaxies wander through space alone, while others join together in clusters. These snapshots of clusters and galaxy mergers give us a glimpse of the dynamic and chaotic evolution of galaxies over time. Just like supernovae, the merging of galaxies drives subsequent generations of stars to form. Our Milky Way, which belongs to a few dozen galaxies called the Local Group, is in the process of cannibalizing other dwarf galaxies. Finally, after 10 billion years, we have reached the Hubble Space Telescope and the end of this light's journey. Hubble is a massive orbiting telescope, roughly the size of a school bus. Its primary mirror is 2.4 meters, or about 8 feet across. Hubble is smaller than many telescopes on the ground, but its position in space gives it many advantages. Ultraviolet wavelengths of light that are blocked by the Earth's atmosphere are accessible to Hubble. The telescope is named in honor of the astronomer Edwin Hubble. In the 1920s, Edwin Hubble unlocked an important part of our cosmic code. He looked at the spectral lines of galaxies and realized the lines he was looking for were not where he expected them to be. The lines were all shifted toward the red part of the spectrum. This red shift meant the galaxies were moving away from us. Hubble was the first person to discover the expansion of the universe. 60 years after Hubble's discoveries, astronomers built the Hubble Space Telescope, which has spent its life observing spectra, our cosmic code. The Hubble telescope is unique in that it was designed to be serviced in space by astronauts. These servicing missions replaced and repaired solar panels, computers, and upgraded the instruments themselves. During the final servicing mission in 2009, the last instrument to be installed on the Hubble Space Telescope by the NASA astronauts was the Cosmic Origin Spectrograph, also known as COS. COS was designed and built by astronomers at the University of Colorado in Boulder, a new spectrograph, 100 times more sensitive than its predecessor. Astronomers use it to identify and map the invisible gas distributed throughout the universe. This gas is fundamental in forming galaxies, stars, planets, and even life on Earth. COS orbits high above Earth's atmosphere and is able to observe the subtle details in the spectra of a quasar's light. Throughout our journey, we have studied ultraviolet light. COS specializes in UV spectra. It turns out that most of the interesting emission and absorption lines to look at in gas clouds and galaxies are in the ultraviolet wavelengths. Let's use what we have learned in our journey to decode the spectrum seen by the Cosmic Origin Spectrograph. The best way to think of this is like an ice core. Ice cores drilled in the Antarctic show layer upon layer of snow and ice. Each layer dates back a year further into the past. COS is also taking cores, but of the universe, with its cosmic fingerprints layered in chronological order. What started out as pristine light has become contaminated by eons of interactions with the surrounding universe. Astronomers embark on the challenging task of differentiating these lines from one another. The quasar is our light source. Its spectrum is dominated by hydrogen emission lines. As the quasar's light passes through cold, distant gas clouds, absorption lines of both hydrogen and helium appear in the spectrum. When the light passed by the galaxy, the spectrum became saturated with spectral features. Based on what we have learned and the tools that we have at hand, we can now extricate the various cosmic fingerprints. We see both heavier and lighter elements, telling us that the stars have been distributing them throughout the galaxies over time. This is a key marker of cosmic recycling. Hubble and COS have sampled hundreds of quasars in many different directions. Each of these cosmic beacons allows us to take multiple core samples of the universe. Astronomers using the Cosmic Origin Spectrograph have been able to decode these samples to see the distribution of elements, their age, their abundance, and the overall structure of the universe. We see clusters of galaxies connected by filaments of gas, and we also see voids in the structure with very few galaxies. This allows astronomers to map where matter is distributed throughout the cosmos. There is elegance to the scientific process. Some astronomers observe the universe with telescopes, while others use computer models to simulate and test our knowledge of physical laws. The goal of astronomers is to test whether their models fit the observations, and vice versa. What you're seeing now is an advanced computer model based on real math and real physics, attempting to simulate the early evolution of our universe. This computer model speeds up time from just after the Big Bang to the present day. You can see the formation of stars, galaxies, and clusters of galaxies. Each of the blobs you see, both large and small, are whole galaxies containing billions of stars like our sun. Watch as galaxies combine and consume each other, forming more massive galaxies. Clusters and groups of galaxies are forming, as well as voids in between them. Let's compare this computer model to the actual observations. What you see before you is the Sloan Digital Sky Survey. This telescope has measured the positions of millions of galaxies surrounding our own Milky Way galaxy. The agreement between the calculations and the observations of the Cosmic Origin Spectrograph excites astronomers who work hard to understand how galaxies formed and how matter was distributed throughout our universe. The Cosmic Origin Spectrograph is helping us unravel the secrets shrouded in the darkness of space. we are beginning to answer many of our oldest and most fundamental questions about the cosmos and our place in it. For millennia, we have contemplated the universe, but our quest to understand the cosmos was limited by what we could see. Throughout human history, cultures developed creation tales centered on the stars. They saw the stars as manifestations of their ancestors. By extending the utmost limits of our telescopes, now we know they were right all along. These stars, galaxies, and invisible clouds of gas are our ancestors, the source of the elements necessary for life itself. When you look up at the sky tonight, don't just look at the stars. Look beyond them and in between. By searching the darkness of space, we have begun to illuminate our own cosmic origins.